This is Mr. Koker, and we're going to do Module 6, Solutions. One of the things about dissolving is that polarity needs to be similar in order to dissolve. There's the old phrase, like dissolves like. So back in the book where it talks about electronegativity, we can see what kind of molecules are going to be polar and will dissolve in water. Polarity is when the attraction that the atoms have for electrons is unbalanced. So when you have an unbalanced attraction for shared electrons, you'll have polarity. The degree that one atom pulls shared electrons to itself is called its electronegativity. Electronegativity increases from left to right, so the metals on the left side of the table have low attraction for electrons, low electronegativity, and elements like fluorine and chlorine and oxygen on the right side of the table have high electronegativities. So in molecules, the atoms with higher electronegativity will tend to be where there is negative charge, and where the atoms with low electronegativity are is where the atoms will be positively charged. Electronegativity also increases from the bottom of the table to the top, and so the top right is actually the highest electronegativity, and the bottom left, francium and cesium, would be the lowest electronegativity. Here are some electronegativity values, so you can see the pattern where electronegativity goes down to the lower left and goes up to the upper right. Notice we do not have electronegativities here for the noble gases because they do not tend to form covalent bonds. So we do not worry about the electronegativity of the noble gases. Just the nonmetals, which are very high. The metalloids are in between, the metals are low. Hydrogen and phosphorus are the lowest of the nonmetals. So when nonmetals covalently bond, hydrogen or phosphorus will tend to be positive. Something like fluorine or oxygen or chlorine would tend to be negative. The atom with the higher electronegativity will be the negative, and the atom with the lower electronegativity will be the positive. If the electronegativity differences are greater than 1.8, that usually signifies an ionic bond, where electrons have actually transferred and you have a plus and minus charge, ionic. Generally in this class you don't need to keep an electronegativity chart around. If you have carbon and hydrogen, or carbon-carbon, or any two elements that are sharing or any two atoms that are from the same element, you can assume those bonds are nonpolar, but other covalent bonds between two nonmetals, such as a carbon-oxygen or an oxygen-hydrogen bond, generally we assume that those are polar. So carbon-carbon, hydrogen-hydrogen, oxygen-oxygen, nitrogen-nitrogen, or carbon-hydrogen, nonpolar. Any other combinations of two nonmetals we usually assume are polar, and they are not sharing equally. So the phrase like dissolves like is where this applies to electronegativity applies to solutions. Polar things like water and ionic sodium chloride and methanol with an OH group on it and acids, polar things dissolve in water, and nonpolar things like oil or octane from gasoline or hexane or paint thinner, these tend to dissolve in nonpolar substances. So like dissolves like. A solution is any mixture of two or more compounds or elements. In any ratio, it needs to be a homogeneous mixture. The solvent is the larger part of the solution, and the solute is the smaller part. A solution can be a solid, a liquid, or a gas. In a solution, the solute is uniformly distributed in the solvent. In other words, it's homogeneous. So we see the picture of a person dissolving salt in water. That would be a solid dissolving in a liquid. If carbon dioxide is dissolved in water to make sodas, that's a gas dissolving in a liquid. Air can be considered a solution of oxygen dissolved in nitrogen, so a gaseous solution. A solid in a solid might be an example like brass, where zinc and copper dissolve together. Let's practice identifying the solute in each of the following solutions. If you put 2 grams of sugar and 100 milliliters of water, or 60 mils of ethyl alcohol with 30 milliliters of methyl alcohol, or 55 milliliters of water with 1.50 grams of sodium chloride, the solute is going to be the one that is the lesser amount. And so the 2 grams of sugar would be less than 100 milliliters of water, so sugar would be the solute. 30 milliliters of methyl alcohol would be dissolved in 60 milliliters of ethyl alcohol, so methyl alcohol would be the solute. 1.5 grams of sodium chloride dissolved in 55 milliliters of water, so the sodium chloride is the solute. In the case of air, 200 milliliters of oxygen dissolved in 800 milliliters of nitrogen. That makes oxygen the solute. So how does water work as a solvent? It's a very common solvent. It's technically really not what some people call it, the universal solvent. Water does not dissolve everything. It only dissolves polar substances, but it's a very good solvent for polar substances. But water will not dissolve oil or gasoline, so it's not the universal solvent. But it is a very common solvent. And here in the diagram we see that the hydrogens are partially positive and the oxygen is partially negative. So the oxygen being more electronegative than the hydrogen, and the shape of the water being in a V shape, make it a polar molecule. Water with its partial negative oxygens can attract positive ions on a sodium chloride crystal. Those would be the sodium ions. Pull it out of the crystal and then surround the sodium ion. And at the same time, the hydrogen part of the water, the positive end, can attract the negative chlorides. Pull those out of the crystal and then surround them. The surrounding of the ions with water molecules is called hydration, and it's a very important step in dissolving because it keeps those ions from going back into the crystal. When you have ions in water, any solution that produces large amounts of ions in water is considered a strong electrolyte. We call it an electrolyte because the solution, the liquid solution, will actually conduct electricity. As you can see by the electrical conductivity tester and the light bulb lighting up, the sodium ions can bring positive charge to the negative electrodes. The negative ions can bring negative charge to the positive electrode, and as a result help the electricity flow through the solution. There are some solutions, such as weak acids, that are considered weak electrolytes. They only produce a few ions in water. They only dissociate partially in water, and so they will light the light bulb dimly, but not as brightly as something like a strong electrolyte. Non-electrolytes, like sugar, dissolve in water, but they don't break up into ions. They don't ionize, and so we would call sugar a non-electrolyte. Does not light the light bulb. If we write dissociation reactions, which is really just the reverse of what we did when we put ions together to make ionic formulas, we're going to list the separate ions and their charges. The subscripts in the chemical formula of the ionic compounds are going to end up becoming the coefficients in the balanced dissociation reaction. So for example, K3PO4 solid, when it dissolves in water, breaks up into 3 K pluses. Now they are aqueous, AQ, and 1 PO4 minus 3, which is also aqueous. And so we see that the subscript 3 on the K became the coefficient 3K plus when we wrote it as a dissociation reaction. PO4, being a polyatomic ion, does not split up into separate ions, and so we do not write the PO4 as separated because it's polyatomic. Solubility is the amount of solute that can dissolve in a solvent. If a solution is holding less than the amount of solute that it's capable of holding, we call it an unsaturated solution. And a saturated solution is one that is holding the maximum amount of solute. In the case of a saturated solution, adding more solute will just cause it to collect on the bottom of the container because the solution is already full of solute. It cannot dissolve more. Solubility can be changed by changing temperature. Here we see a variety of solids and their dependence on temperature. Generally, as a solid's temperature goes up, as a solution temperature goes up, the solid will dissolve better. There's only one example here on this diagram, sodium sulfate, where it actually goes down with higher temperature. But generally, solids are going to increase in solubility as temperature increases. So that's one way to increase the solubility of a solid, is to heat it. Solubility of gases decreases as temperature increases. And so gases dissolve less at higher temperatures. Gases will dissolve better at higher pressures, though. That's called Henry's law. If you think of a Coca-Cola can of soda, the soda is under pressure, allowing more carbon dioxide to be dissolved in the water. Here are some solubility rules for various groups of ions. Notice there are some ions that are always soluble. It doesn't matter what opposite ion you put with it. For example, the alkali metals, sodium, potassium, lithium. Also throw in that group ammonium, which is a polyatomic +1 ion. These ions are always soluble. Nitrates and acetates are also always soluble. Ions from group 17, the halogens, are also soluble with a few notable exceptions. Silver, mercury 1, and lead 2 form insoluble precipitates with the halogens like chloride, fluoride, iodide. Sulfates are soluble, but they have a few more exceptions: strontium, barium, calcium, and lead. Sulfides are soluble unless they're paired up with strontium, barium, or calcium. Hydroxides are slightly soluble. Soluble pretty well with the alkali metals, but with strontium, barium, and calcium, they're only slightly soluble. Generally, anything else besides these ions, you can always assume that they are insoluble, unless they are with a soluble ion. There are always two ions in a formula, right? So you got to check the solubility of both ions. The math in this chapter deals with concentrations of solutions. Concentration being the amount of solute in a particular amount of solution, or the amount of solute paired up with a certain amount of solvent. There is a mass percent that is commonly used by non-scientists. It's the percent of mass to mass. Remember, percents are part over whole, and then the part over the whole is multiplied by 100. So mass percent concentration, percent by mass, is going to be grams of solute divided by grams of solute plus grams of solvent, and then that ratio multiplied by 100. In other words, mass percent is how many grams of solute you have in 100 grams of solution. So if you're thinking about factor label problems, grams of solute over 100 grams of solution makes a good conversion factor. So we call it mass percent M over M because we have mass on top and mass on bottom. Calculating it requires knowing both the grams of solute and the total grams of the solution. So let's say we had a KCl solution. Let's say our KCl solution has 8 grams of KCl and 42 grams of water, giving us a total of 50 grams of solution. The mass percent would be 8 grams of KCl over 50 grams of KCl solution times 100, which calculates out to be 16% M over M. Here's another example problem. A solution is prepared by mixing 15 grams of sodium carbonate with 235 grams of water. Find its mass percent. Step 1, our solute is 15 grams. Our solution is 15 plus 235, or 250 grams. Find the gram of solute to gram solution ratio by taking 15 over 250 and then multiplying that ratio by 100 gives us that the solution is a 6% mass over mass solution. Sometimes when you're mixing two liquids, you do a volume over volume percent. Percent volume over volume is when you take the milliliters of solute to the milliliters of solution. So generally this is when you have a liquid solute like alcohol and water. So it's not grams over grams, it's milliliters of solute over milliliters of solution, then that ratio times 100. So it's very similar to percent mass over mass, except it's volume over volume. We have to total the volumes of the solute and the solvent to get the volume of the solution. So if a chemist adds 30 milliliters of NaOH to 225 milliliters of water, the volume by volume concentration is going to be 30 milliliters plus 225 milliliters is 255. 30 over 255 times 100 is 11.8% volume over volume. There are cases where we mix these two units and call it mass over volume percent. That's when you have the percent mass of grams of solute to volume of solution. So it's the grams of solute over milliliters of solution. In this case, they will have to give you the total volume of the solution because you cannot add the mass of the solute to the volume of the solvent and get the milliliters of solution because they're not the same unit. If you have 25 grams of potassium chloride and you're adding it to enough water to make 300 milliliters of solution, the percent mass over volume is going to be 25 over 300 times 100. So the mass is the mass of the solute, 25 grams. 300 milliliters is the volume of the solution. So 25 over 300 times 100 equals 8.3%. So understanding the percent mass over mass, percent mass over volume, and percent volume over volume units allows you to solve some problems with these conversion factors, such as this conversion factor, 25 grams of KCl over 300 milliliters of solution. That can be used to solve a problem if it's used as a conversion factor. So there are actually two conversion factors that can be written for each type of percent value. Let's say you have a 10% mass over mass KCl. You could use the conversion factor 10 grams KCl over 100 grams of solution, or you could flip it and have 100 grams of solution over 10 grams of KCl. A 5% mass over volume glucose solution, could give you a conversion factor of 5 grams of glucose over 100 milliliters of solution, or 100 milliliters of solution for every 5 grams of glucose. Likewise, a 12% volume over volume ethanol solution would be 12 milliliters of ethanol over 100 ml solution, or 100 ml solution over 12 milliliters of ethanol. Choose which conversion factor helps you solve the problem. Let's practice writing conversion factors. I have an 8.5% mass over mass NaOH solution. That's 8.50 grams of NaOH over 100 grams of solution, or 100 grams of solution over 8.5 grams of NaOH. 5.75% volume over volume ethanol solution is 5.75 milliliters of alcohol over 100 milliliters of solution, or 100 milliliters solution over 5.75 milliliters of alcohol. 4.8% mass over volume HCl solution means you have 4.8 grams mass of HCl over 100 milliliter solution, and you also have 100 milliliters of HCl solution over 4.8 grams of HCl. So now we can use these conversion factors to solve some problems for preparing solutions. Let's say I want to prepare 225 grams of a 10% mass over mass NaCl solution. I want to make 225 grams of solution, and my concentration needs to be 10% mass of NaCl over mass of solution. I need to find out how many grams of NaCl, and so I want to go from grams of solution to grams of NaCl. I have two conversion factors, 100 grams of NaCl over 100 grams of solution, or 100 grams of solution over 10 grams of NaCl. The first conversion factor actually helps me solve it because I want to start with 225 grams of solution and multiply by 10 grams of NaCl over 100 grams of solution, so the grams of solution cancels out. 225 times 10 divided by 100 is 22.5 grams of NaCl. So the question was, how many grams of NaCl are needed to prepare 225 grams of a 10% mass over mass NaCl solution? The answer is 22.5 grams of NaCl. Of course, practice makes perfect, so let's try more examples here. How many milliliters of a 5.75 volume over volume ethanol solution can be prepared from 2.25 milliliters of ethanol? Now in this case, we are given the solution percentage and we're given the milliliters of the solute. So in this case, we are going to use the flipped version of the conversion factor. 2.25 milliliters of ethanol times 100 milliliters of solution over 5.75 milliliters of ethanol. So we inverted the 5.75 volume over volume ratio. 2.25 times 100 divided by 5.75 is 39.1 milliliters of solution can be made from 2.25 milliliters of ethanol. How many milliliters of a 4.2% mass over volume solution will contain 3.15 grams of KCl? So once again, we are given the mass of the solute, so we are going to use the flipped or inverted conversion factor. Because we start with grams of KCl, we want to take the second conversion factor. 3.15 grams of KCl times 100 milliliters KCl solution over 4.20 grams of KCl is 75 milliliters of KCl solution. 75 milliliters of the solution will contain 3.15 grams. Now, a more chemist conversion factor is the molarity unit that you learned about in Chem 1. It's a concentration term used by chemists for solutions. Molarity gives the moles of solute per liter of solution. If you have 2.6 moles of sodium carbonate in 1.3 liters of solution, then you have a 2.6 to 1.3 ratio, or a 2 molar solution of sodium carbonate. A 1 molar sodium chloride solution would be prepared by weighing out 58.5 grams of NaCl, 1 mole, putting it in a volumetric flask. These are the special flasks with the very narrow necks and the line that signifies a particular volume. In this case, that would be the 1 liter volumetric flask. Then what you're going to do is you're going to add water until it's all dissolved, and then finish filling it up to the line so that you have exactly 1 liter of solution. So it will contain 1 mole, 58.5 grams of NaCl, per liter of solution. What's the molarity of 0.5 liters of NaOH if it contains 6 grams of NaOH? Molarity, remember, is found by dividing moles by liters. So our first step is going to be to change the grams of NaOH to moles. I'm going to use the conversion factor 1 mole of NaOH over 40 grams and multiply it by 6 grams. 6 grams of NaOH times 1 mole over 40 grams is 0.15 moles. So 0.15 moles over 0.5 liters is my moles over liters, which comes out to 0.300 moles over 1 liter, or 0.300 molar NaOH. So the molarity of half a liter with 6 grams of NaOH is 0.3 molar. Another one, what is the molarity of 325 milliliters of solution containing 46.8 grams of NaHCO3, sodium bicarbonate? This was worked exactly like the last one. 46.8 grams times 1 mole over 84 grams, 84 being the molar mass, would get, when you add up 23 sodium plus 1 hydrogen plus 12 for carbon and 3 times 16 for oxygen. You add up the molar mass, you get 84. 46.8 divided by 84 is 0.557 moles. 325 milliliters is 0.325 liters, so moles per liter is 1.71 molar sodium bicarbonate. How many grams of KCl are needed to prepare 125 milliliters of 0.72 molar KCl? This is a little different. We are trying to go from molarity and volume to grams, and so we're going to take the liters of the KCl, multiply it by the molarity to get the moles of KCl, and then multiply that by the molar mass to get the grams of KCl. First, we're going to find that a mole of KCl weighs 74.6 grams. And then a liter of KCl has 0.720 moles of KCl in it. So that actually, the molarity unit of 0.720 molar can be written as 1 liter over 0.720 moles, or 0.720 moles over 1 liter. So if we start with the liters, 0.125 liters, change it to moles by multiplying by the molarity, 0.720 moles over 1 liter, and then change the moles to grams by multiplying by 74.6 grams of KCl over 1 mole, we get that we're going to need 6.71 grams of KCl. Second, let me get our place found again. Plugging in the values, we get 1.5% is the new solution concentration. This slide isn't very good because it changed where the location of the calculated values are. But if you'll take C1 and V1 and C2 and V2 and plug it into this formula, C1 V1 equals C2 V2, and solve for C2, I think you'll see that you get 1.5% mass over volume. So a second here. Some examples could be salt water, sugar water, air, alcohol and water. All of these examples fit this particular description of solutions. On the other hand, colloids are when you have medium-sized particles, usually 1,000 nanometers in size or so. Unless you have very specific scientific filters, these are generally not filterable by paper filters like we use in our labs. But semi-permeable membranes can be used to separate them. So in other words, something like dialysis tubing can separate it. Colloids scatter light via the Tyndall effect. Some examples of colloids are like fog. Think about how your headlights are scattered as the light tries to pass through the fog. Whipped cream, milk, cheese, blood plasma, pearls. These are examples of colloids. A lot of colloids are whitish in color, or cloudy. So think of the word colloids, think of cloudy. Suspensions have very large particles. In fact, suspensions are large enough particles that they will eventually settle out. So you think like soil and water and how the soil settles to the bottom of a bucket of water, muddy water. The dirt is going to settle to the bottom. That's an example of a suspension. Suspensions can also be cleaned up by filtering them. You have to keep a suspension stirred in order for it to stay suspended. So like the muddy Mississippi, the movement of the water stirs up the dirt on the that's in the water and keeps it suspended. But when the water stops moving, when it reaches the Gulf of Mexico, then the dirt settles out and you have the delta at the mouth of the Mississippi. Blood platelets, muddy water, calamine lotion, any medicine that says shake well before using would have to be in a suspension. Diffusion and osmosis are properties of solutions that affect the cell, and so it's important in a medical chemistry class to talk about diffusion and osmosis. Diffusion is simply particles moving from areas of high concentration to low. You think about a perfume bottle being opened, the odor will spread throughout the whole room. So that's simply because in a gas or a liquid, molecules can move past each other and spread out, and will spread out randomly. Osmosis is a special type of diffusion where water is the one moving, and the water is moving from high concentration to low, typically into a cell or out of a cell. The water is going to move through a semi-permeable membrane, such as dialysis tubing or the cell membrane, and the water is always going to move to the area where there is more solute, because the water, if the solute has a higher concentration, the water has a lower concentration. So we're talking about water moving from low concentration to high. The semipermeable membrane is a membrane that allows some materials to pass but not all. So typically a semipermeable membrane is going to let water pass but not the solute. Let's say we have starch and water, and we have two solutions, a 4% and a 10% solution, and we have the two solutions separated by a semi-permeable membrane shown as a dotted dashed line here. Water is going to try to move out of the 4% starch solution into the 10% starch solution until both solutions are a 7% starch solution. Water is going to try to equalize the concentration by moving from the 4% to the 10%. So this will cause the water level to rise on the right side and lower on the left side. Once it reaches a point where there's a 7% starch solution on both sides, the water will be at equilibrium and will be moving between the two sides at an equal rate, equilibrium. Starch, being a colloid, cannot go through the membrane, but water can. So what ends up happening is osmosis occurs, and you get a pressure which raises the water level on the right. If we consider the pressure to be a type of osmotic pressure, osmosis pressure, we have terms for solutions that cause the water to move in different directions. For example, an isotonic solution is one where the concentration of water is the same on both sides of the barrier. A hypotonic solution is a solution that has less solute and so more water. Water will tend to move out of a hypotonic solution. Water will tend to move into a hypertonic solution because the solution has more solute. And because it has more solute, it has less water. Make sure you read the pages in the book about isotonic, hypotonic, and hypertonic.